So to talk about shapes of molecules, the simplest theory is called VSEPR theory. And that VSEPR stands for valence shell electron pair repulsion. So this is the idea that electron groups repel each other. Yes?
That's what worksheet 9 is on, right?
So it's important that we get straight what we think of as an electron group. An electron group could be a lone pair of electrons. It could be a single bond, a double bond, a triple bond, or a single electron. So a group of electrons is not a pair of electrons, even though the name suggests that, electron pair repulsion. We need to think of them in terms of groups, okay? So the repulsions between electron groups on the interior or central atoms is what determines the geometry. So here we have an example. There's a central atom, a single bond with this atom, a single bond with that atom, a single bond with this atom. These groups forming those single bonds are going to repel each other. And that's what determines the shape of the molecule. The preferred shape or geometry is going to have a maximum separation of electron groups because that's the minimum energy. So my mom brain says this is like traveling in a minivan with your children, right? If you got 3 kids in the minivan, do you want them all in that back seat sandwiched right next together? You guys have siblings? Is that a good idea? No. You're breathing on me. He doesn't smell good. He farted. You know, he's just bicker, bicker, bicker. What are you going to do? You're going to spread those little darlings apart, right? Get them as far away as possible from each other so that their interactions are going to be minimized. Well, you know, you'd like to send one to Ohio, but that's not possible. They have to stay in the minivan. So you just do the best you can, right? So that's what we're doing here. These electron groups are all attached to the central atom, so we can't just send this one over here. They all have to stay attached to the central atom, but they can get away from each other by being on opposite sides of the central atom. That make sense? So that's the basic idea behind VSEPR theory. So we're going to look at the 5 basic shapes one at a time. So let's look at the Lewis structure for beryllium chloride. And this is kind of an odd one. So we would put beryllium here and put a chlorine on each side. And then we look at the number of valence electrons. Each chlorine has 7, so 2 of those is 14. And then the beryllium is got 2. So that's 16 electrons. So we got 2, 4, 6, 8, 10, 12, 14, 16. And at first glance, that doesn't look like a good Lewis structure, does it? Because we don't have an octet on beryllium. Does beryllium always have to have an octet of electrons? No, beryllium is small. If we evaluate formal charges, we'll see that this is the correct structure for beryllium chloride. Okay? So we start with the Lewis structure, and then we look at the central atom, and we ask ourselves how many groups? How many electron groups? Single bond, double bond, triple bond, lone electron, or lone pair. Each of those counts as one group. So on this beryllium, we have 1, 2 bonds, single bonds. So that's 2 electron groups, right? So how do 2 electron groups get away from each other? Well, I have balloons. There's 2 balloons tied together. What are they doing? If you look at the knot holding them together, they're going to spread apart, right? They're going to be on opposite sides. So they're going to take this shape. So the chlorine atoms are going to be on opposite sides of the beryllium atom. There's only 2 of them, and so they can get on opposite sides. Another way to think about this might be that this is you, And this is that X who really broke your heart, right? I mean, he or she, just nasty to you, just really, really bad, the worst. So this is the planet Earth, and here's you, and there's your X. You want to maximize the space, you're going to be on the opposite side of the planet. Can't get any further away than that, right? It makes sense. So that's what these two things are going to do. When we talk about the geometry of the molecule, we're going to look at the arrangement of the atoms. Not the electron groups, but the arrangement of the atoms. So we look at this, we determined how they're going to be shaped because of the electron groups, but then we're going to look at the atoms. So these are in a line, so they call that a linear geometry. And we can think about the bond angle. So the bond angle would be from this chlorine to this beryllium to the other chlorine. And here the bond angle is 180 degrees. This is what VSEPR theory predicts, and it's confirmed by observation. Let's look at CO2. So if we draw a Lewis structure for CO2, a carbon in the middle, oxygen on each side. Start out with single bonds, but then in drawing it, we realize that we need double bonds. The point of this is not how to draw the Lewis structures, but just to get them done. There's a Lewis structure for carbon dioxide. Look at the central atom. How many groups of electrons? A double bond is one group. Two groups. This double bond is a group, and that double bond is a group. The double bond is 4 electrons, 2 pairs of electrons, but they are stuck between the carbon and the oxygen. They can't move away from each other. So they are together. So two groups are going to arrange themselves on opposite sides of the central atom, and we're going to have a linear geometry as well for this one. So 2 groups, linear geometry. Let's look at BF3. So BF3, we'll put the boron in the middle and put the fluorines around it.
Sorry.
It's okay. And then we put in all our valence electrons. And we end up short of an octet for the boron. Was boron okay with that? Yeah, boron is okay with that. Boron's one of those little guys. It's like, yeah, I like 8, but 6 is fine. It's good enough. The way to confirm that is to look at formal charges. You find that this structure will have 0 formal charges. So it's better than trying to do a double bond and give boron an octet. So here's our Lewis structure. Here's our boron. How many electron groups? 3. There's 3 single bonds. 1, 2, 3. So how do 3 things get away from each other? Here I have 3 balloons tied together. What shape does that make? A triangle. We're not going to have 2 of them on opposite sides and that one squeezed in the middle, right? I can bend it like that, but when I let go, it makes this triangle again. And the reason I've got the balloons here is because balloons are familiar objects. They're fun too, but balloons are familiar objects, and they give us a great visualization for what's going on with these groups that are trying to get away from each other. And so, feel free to try these at home. So it's going to make a triangle. The angle here will be 120 degrees because a full circle is 360 degrees, and so it's divided evenly into thirds, so the angles are 120, getting as far away from each other as possible. So we give this a name. We call it a trigonal planar geometry because these atoms form the shape of a triangle, and it's in a plane, it's flat, right? So you can draw a plane through the nuclei of all those atoms, and they all lie in the same plane. So trigonal planar. Formaldehyde also has 3 groups. Here's its Lewis structure. Not up there, down here. So here we look at this carbon, and it's got a single bond and a single bond and a double bond. That's 1, 2, 3 groups, right? So you think of 3 balloons. What shape do they make? They make a triangle, right? So these atoms are going to spread out around the carbon in a triangle shape. But now these are not all the same, right? Here's an oxygen with a double bond. The oxygen is larger, the double bond is larger, and here we have little hydrogen with his single bond, and these are smaller. So it's going to make a triangle, but it's not going to be perfectly equal. So the oxygen is going to take up a little more space. The angle here is going to be a little more than 120. The angle between the hydrogens is going to be a little less. So it's just not quite perfect, but it is still trigonal planar. Okay? Different types of electron groups exert slightly different repulsions. Any questions? Yeah.
How is that degree of the angle calculated?
That's a good question. How do you calculate this? They observe it. So that's kind of tricky, but they just observe it and they say, okay, well, this is what it is. So you can estimate, but you can't really predict what they're going to be. There's no formula. That's an excellent question. So do I expect you to remember that in formaldehyde the angle's 121.9 and 116.2? Absolutely not. What I would like you to be able to say is that the angle between the oxygen and the hydrogen is going to be a little bigger than 120, and the angle here is going to be a little less than 120. So this angle, you should be able to tell me is less, oops, wrong one, greater than 120, and this one is less than 120, and this one's greater than 120. And so how do you remember that? Well, this oxygen and the double bond is bigger. So if I've got this triangle and one of these balloons is a lot bigger, it makes sense that it's going to take up more space and it's going to cause the other two to squish together just a little bit, right? And so that's what they're doing. Any other questions? 4 groups. Okay, this is harder to visualize because now we're getting into 3 dimensions. So here we actually have pictures of the balloons. So here's the linear geometry, the 2 balloons. Here's trigonal planar geometry with 3 balloons. And the balloons are representing electron groups. They're not representing the atoms. They're representing groups. So when we have 4, if we take this group of 3 balloons and put in another balloon, a 4th balloon, we get this shape. Which, you know, we don't run into that shape very much in everyday life, and so you probably don't have a name for that shape. Yeah, a pyramid is probably the best we can do. The name we use in science is a tetrahedron. A cube has 6 corners. A tetrahedron has 4 corners. Tetra meaning 4. So it's got 4 corners. It's a tetrahedron. Now we're taking 3-dimensional space and dividing it into 4. I don't want to go into the math of that. The bond angles are 109.5. Be great if you can remember that. If not, it's not a huge deal. 109.5, perfect tetrahedron. So here's making it into a solid. That would be a triangular pyramid, right? It's a pyramid where the base is a triangle. So it's a tetrahedron. So if we look at methane, here's the Lewis structure for methane. There aren't any lone pairs anywhere on that one. You look at the central atom and you see it has 4 electron groups, 4 single bonds. So how do 4 things get away from each other? They form a tetrahedron like the 4 balloons do. So here we've got the carbon is in the center of the tetrahedron and the 4 electron groups are spreading out evenly spaced in 3 dimensions. And so the angles between them will be 109.5. When we draw the Lewis structure, it looks flat, doesn't it? It looks square and flat. But that's not what the molecule does. So hopefully this will work. we can take our balloon tetrahedron and we can make it flat, but you disturb it at all and it pops back into a tetrahedron because they're squished together, right? So in this, we would have 90-degree angles. If it forms a tetrahedron, it can have 109.5-degree angles. These electron groups are repulsive to each other. They're like, ew, ick, I want to get away from you, right? The lowest energy state is where they're as far away as possible. And so that's in the tetrahedron. Okay? What if we stick 5 in? So if you put in a 5th balloon, it's going to push these out of the way. So here we've got 5 balloons. They're a little wet. So I think of this as a little bit like a girl wearing a tutu. So here's her head, the balloon on top, and here's her feet on the bottom, and then the 3 balloons around the middle are like a tutu, and she can do ballet and spin around and twirl her tutu, right? It's important to be able to see that the angles here are not all equivalent. So here we have a ball and stick model of that shape. Here's the little girl's head, and here's her feet, and this is her tutu around the middle, right? So the angle between the head and the tutu is 90 degrees, and between the tutu and her legs is 90 degrees. But the angle between those 3 balloons that are making up the tutu, those are arranged in a plane, 3 objects in a plane, those are 120 degrees. So we have 2 different angles. And this structure is called a trigonal bipyramid. Trigonal bipyramid. It's a triangular pyramid, but it's 2 of them. So if you look at this, here we've got a triangular pyramid on the top and a triangular pyramid on the bottom. So it's a bipyramid, 2 pyramids stuck together. So this is what happens when we've got 5 electron groups, as we do for phosphorus pentachloride. So 5 things will make this trigonal bipyramid. The 3 groups that lie in a plane, the girl's tutu, are the equatorial positions. So those are like around the equator of the Earth. And the 2 groups above and below that plane are called the axial positions. So they're like the North and the South Pole. So the North Pole, the South Pole, and then this is around the middle, the equator. So axial and equatorial. Put 6 balloons together. I don't have that one made up. You put a 6th balloon in here, and they're going to squeeze together a little bit more, and you're going to end up with an octahedral geometry, an octahedron. So this has 4 equatorial groups and 2 axial groups. But the distinction here is not as important because now with 4 groups around the equator, the bond angle there is 90 degrees. And the bond angle between the equatorial and the axial is also 90 degrees. So all the bond angles are the same. An example molecule for this would be sulfur hexafluoride. It's got 6 single bonds. Any questions? Okay, so determine the molecular geometry of carbon tetrachloride. What we're going to do is we're going to draw the Lewis structure and look at the central atom and ask ourselves how many electron groups. And then we're going to think about balloons. So carbon tetrachloride, put the carbon in the middle and put the chlorines around it. And then if we distribute all of the valence electrons, we'll find out that its Lewis structure looks like this. So you start with the Lewis structure. Look at the central atom. How many electron groups? 4. There's 4 single bonds. So we have 4 electron groups. Well, if we had 4 balloons tied together, what shape would they make? A tetrahedron. So this is going to be a tetrahedral geometry. Any questions? The Lewis structure looks flat, but the molecule is not.